I work for a company called Particular Software. I'm Daniel Marbach. I'm coming from Switzerland. Particular Software we are the makers of Service Bus. It's basically a .NET Service Bus messaging abstraction library. But I'm not here to talk about Service Bus because before I joined Particular Software, I was working for a consultancy company in Switzerland. And as part of that consultancy company, obviously we consulted with a lot of customers. And one of the customers that I was working with for multiple years, we were tasked to basically build a medical invoicing system. It was we were handling probably 4 million patient records of 4 million patients in Switzerland from different doctors. But we also did, for those doctors, we actually did the medical invoicing. So basically, when you go to the doctor, you got an invoice for all the things that you did together with the doctor, like first 5 minutes, second 5 minutes, last 5 minutes, some treaties that you got from the doctor. That's what we were responsible for. And that system was written around the .NET 1 time frame and gradually evolved over multiple years. So the system was running for over 10 years. It was running on 13 different servers. We had SQL servers. Had all kinds of problems. You would probably call this a legacy mess, but hey, it was thriving, it was making money. So, but then one day the customer came and said, well, we're doing medical invoicing. Wouldn't it be cool if we could expand our business to do general purpose invoicing? Especially web shops. We could do invoicing for all web shops out there. And we were like, the development team were like staring at the customers like, no, and he was like, come on, you're smart people, you can do this, right? But hey, just one little constraint, I don't have a lot of money, but can you please make it happen? Has it happened to you as well in your project? Never, exactly, exactly. And you're scratching your head like, how can we make this happen? Well, but one of the things that we knew is, once we are transitioning from this medical invoicing type of stuff where doctors have their opening hours and we have a lot of downtime during the night where we can do batch processing and all that stuff, we knew that once we were opening the world to the web shops, we essentially have a problem because you right now in this talk, you're sitting here and it's like, I want to buy this new amazing phone, Android phone or iPhone or whatever. You can open up your cell phone, you can browse your favorite web shop of the day and you can order right now a new cell phone, right? Maybe you want to discuss this with your significant other before you do those type of money spending, maybe not, but I'm saying you can do it right now, right? And we realized that with the current architecture, we have a lot of temporal coupling between the front-end services and the back-end and the database. So if one piece of the puzzle fails, everything fails, and that means it ripples up through the call stack to the web shops, and then we are, so to speak, screwed, right? So we said, well, we need to address the temporal coupling, and we also need to address the temporal coupling not only from an availability perspective for the web shops, but also for us, because we want to have a maintenance window, because we knew we had a lot of legacy components down there that sometimes we needed to bug fix, sometimes we needed to update a tiny little library that was already 3 major versions out of date, but still, we needed to do those kinds of refactoring, redesigns, and gradual changes to the system. And so what we said is, okay, we can do this, but we start with a really small use case. So what we did is we talked to the customer and said, well, one thing that we can start first is invoice refunding. How about we do that? Because that's a service that we can offer to web shops already today. We can use it as a gradual transition to actually start evolving the system. Because we were also quite sure that we can't like microservice the shit out of the system, right? Because in no project that has a certain age, that has a certain million lines of code, you can go today, make a decision together and say, we're going to re-architect everything. And then we have the only one requirement, it should do the same as before. And also extend new feature, right? That never works, at least in my experience, it never works. Maybe you have different experience. So this is the architecture that we came up with. So we had our rusty, old, but nicely working WCF services in the front end. That's on this side, and then we had our backend service, and we said, well, in order to address temporal coupling, how about we introduce a message queue in the middle? And the message queue, because we were already quite heavily bought into the Microsoft ecosystem, .NET, C#, Windows, we said, well, let's use MSMQ because it just works. It's out of the box there. So what we did is essentially instead of going from the front end over .NET remoting, yes, we still use .NET remoting, to the backend and then directly to the database, we introduced that queue down here, and we said, how about we take the invoice refund, package it into a command, send it into that message queue, and then we report back to the web shop that is constantly polling us, right? Because they want to have apparently in some of the web shops infrastructure, it's quite common that you just pull the shit out of the system, hoping that the system behind the scenes is then faster. I don't know, but that happened to us. So they were constantly polling us for the invoice refund state. So we introduced a query cache, where we essentially faked the state of the invoice refund directly into the demilitarized zone, into the cache, and then we sent the refund command into the queue, and then the backend was listening on that queue, was receiving those messages when it had time, when it was online, and then what it did, it communicated with our SQL server, it did the reads and writes, did the execution of the business logic, and once that was done, it published an invoice refunded event. And that went into the queue or into the messaging cluster, so to speak, was then caught up by a subscriber that was living in the demilitarized zone over here, did update the front-end query cache, and then in the next iteration, when the PHP client or the WooCommerce client or whatever technology that our customers were using came back again, we could say, hey, by the way, here is your invoice refund state. So with that, we essentially got a really nice temporal decoupling, because we're no longer temporally coupled to the availability of the backend, no longer temporally coupled to the storage. And we got some really good scaling vectors in our architecture, because we could essentially say at any point in time when we're reasonably certain that the piece that is responsible to do the invoice refunds can be scaled out, we can just pull it out into its own process. It will listen to the queue, and we can horizontally scale it if we want to do competing consumers. We have throttling capabilities. For example, when we knew that the DB was, for some contingent reasons or something, not really coping with the load, we could, for example, introduce throttling characteristics and then only take as many messages as we could handle. And but actually the biggest win was the intent capturing messages, right? So we had this intent captured of the invoice refund, we put it into the queue, and then we took it out, the intent out of the queue, and when something went wrong, for example, we had sometimes DB timeouts, not really good transaction handlings, or we had like legacy problems in there as well. Some of the views and indexes that we use weren't yet optimized. We're still working on optimizing that stuff. Then we got transaction rollbacks. We could essentially handle those messages multiple times until we were done. So we were like fully bought into this architecture approach, and we said, let's try to do this. But then we had a really tough decision to make, and that was really, okay, so we need to communicate with MSMQ. We have a bunch of business logic, and we need to write some message middleware, message abstraction thing, so that every developer in the projects can use this stuff. So do we build it ourselves, basically? Like go into the dark and do it, or do we buy something or use something off the shelf? Some open source product, some commercial product, it doesn't really matter. And then well, in this project that I talked about, we actually bought something, used something off the shelf. In another project, we actually built something ourselves. And we said, well, after all, it can't be that hard of a problem to solve. And I want to talk to you a little bit about the problems that I faced when doing that, and hopefully so that you can learn something when you ever tasked to build a messaging abstraction library yourself, you know what you have to deal with. But before we do that, we have to talk about the basic things that a messaging abstraction actually needs to do. So one of the things that we needed to do was the sending part. It's over here. So whenever we got an invoice refund.cf call, we actually packed that intent into a message, and that message had to be serialized over the fancy serializer of the day, which was SOAP. but today is probably something else. And we package that, we send it to the destination queue, to the input queue, and then on the other side, we need something that receives messages from the queue, does that in a reliable way, and once it's done, we're publishing events again. And obviously, one of the important aspects of the receiving part is also that once you get a message, we need to be able to find out based on the message type to which business logic actually that message type belongs, and then execute the right business logic. Okay, so that sounds super simple. Let's see some code. And I'm going to show you the first iteration, the first version of the message pump that we built. So here is a bunch of code on my slides. Don't worry if you don't understand it all. I'm going to zoom in a little bit in those different pieces. So first of all, if you're receiving something from a resource like a queue, we need to start that receiving loop. So we have a receiving loop, and what we did there is we had a cancellation token, source cancellation token, to be able to tell the loop when we're stopping the system, we're shutting down the system, hey, please stop fetching stuff from the queue. So pretty simple. Then we have a pump task, and inside the pump task we have a while loop, and that while loop just churns messages. Then what we did is we had this read from queue method, which, for example, returns a memory of byte, or if you're using some more modern stuff, you could be using system IO pipeline, system threading channel. Here I'm just illustrating a really simple approach for the sake of this demo, right? And then we're reading stuff from the queue, and usually what we get from the queue is a payload, which is basically the business intent, and some headers. And the headers is basically, like in HTTP, some metadata that is associated to that payload. Right? That could, for example, be a tenant ID, or, for example, the application type of the thing that you're sending, so that the deserializer knows it's XML, it's JSON, which deserializer to use. And then what we do is we take this raw information that we get from the queuing system, and we turn it, deserialize it into a message. We call that logical message, but it's basically an instance of a class that you as a developer define, right? And then we dispatch the business logic, which is illustrated here with this await handle message method. I'm showing here a polling approach, right? And depending on, for example, the underlying SDK that you're using, it could be that the SDK itself already has higher level semantics that are more push-based, but it doesn't really matter because under the hood, they're also probably doing some kind of polling, right? Just that you get the gist of it. And also some transports that you're going to use, they actually differentiate between payloads and headers, and some transport don't have that concept. So you're basically tasked to write that logic yourself should you need headers. And most queuing systems actually need headers. Let's zoom into the handle message. Here for the demo purposes, I'm just doing an await task delay to spin some cycles for 1,000 milliseconds, and then I'm writing something to the console, nothing fancy. Let's look at the stop. So what we're doing in the stop is we're basically saying, well, I give you 5 seconds time to shut down, and then I wait until you are done, until you're done pumping, right? Because we want to do a clear shutdown, and then I dispose all the sources that we have. So that's the receiving part. Pretty simple. I'm not going to talk too much about the sending part, because the sending part is pretty simple, because what we're essentially doing, we're taking an instance of a class, which is the logical message. We serialize it into some payload, JSON, XML, SOAP, whatever, and then we send it with the headers and the payload to the destination queue. Obviously, we need to figure out to which destination queue we need to send it, but that's pretty much the sending part. So let's do a brief recap what we just saw in this code example. So with a little bit of, let's say, task parallel hand waving, a little bit of corporative cancellation.NET 101, and a little bit of async sprinkle magic, right? We were able to build a pretty robust and reliable message pump that is able to receive messages from a queue, and this worked really nice. So, until something happened. The business was working fine, and there was this freaking rush hour. What does it mean? Well, so some of the web shops basically had precious items that people were getting, and a lot of people were trying to buy it. So the queue started filling up with commands, and our pump did something really special. What it did was, it basically took one message out of the queue, executed the business logic until it was done, and once it was done, we took out the next message out of the queue, right? So what it means is, if the handler takes, for example, because of DB transaction stuff, because of latency and whatever it takes, let's say 5 seconds, if we have 3 messages in the queue, essentially the last message in that queue will only be handled after more or less 10 seconds. So what we can say here is, with that really simple version of the message pump, our critical time, which is a metric that is quite popular in the queuing world, went through the rooftop. What is the critical time? Well, the critical time is basically a combination out of 3 metrics. One is the network send time. So that's basically the time that you spend on the network until the payload and the headers arrive in the destination queue. And then what we have is we have the so-called queue wait time, which is the time the message sits in that queue and is not yet received. Again, with the example of 5 seconds, the last message queue wait time would be at least 10 seconds, right? And then what we have is the processing time, which is the 3rd metric. And the processing time is the time it takes the pump to detect that something is in the queue, take it out, and then execute your business logic, and then the whole business logic execution and until it's acknowledged or not acknowledged, right? Depending on the outcome of the message handling. So the critical time was a problem in that really simple implementation. So let me briefly show you a demo of the previous code that I showed, illustrated with a console application, how it looked like. So we can really see that if it takes a second to get a message out of the queue and handling it, we get every second a new message, right? That was the problem that I was trying to illustrate. And because we're developers, we said, that's easy to solve, right? We can deal with concurrency. Let's throw in some concurrency, and let's unleash the concurrency. So what we did is we created a new version of this code. So we did a tiny little change, and I'm going to zoom in on this change, which is essentially this one. This is the piece of the puzzle. So instead of awaiting, because remember, await means let's sequentialize here, do not block any thread, and once it's done, continue executing. Right? When we remove the wait statement by introducing this method here, fire and forget, and by the way, that's just an extension method that accepts a task and does nothing with the task. A similar code example would be if you write _equals fetch and handle message, because you're not doing anything with the task. That's what we did. That's what we changed. The rest is essentially pretty much the same. We just took the code that was previously in the loop, we took it out, put it into this fetch and handle message method, but the code is exactly the same. The shutdown logic in this example is, I'm going to highlight this little piece here. The cancel after is now no longer 5 seconds, it's just 100 milliseconds for the sake of this demo. I'm going to cover it later, why I used 100 milliseconds. And then we await the task and that's it. So we said, well, this is just a tiny little change, and it makes sense. We introduced this fire and forget and said, let's ship it. We don't need to do a lot of Q&A. We can manually review this. It's going to be fine. Well, this worked pretty well until we had, again, this freaking rush hour, and which is kind of an oxymoron, right? Because we're saying the business is making money. And because the business is making money, we're actually tripping over with our infrastructure. And life would be so much easier if we didn't have this problem, if we didn't have customers coming to us and creating that problem. But actually, we're trying to make money, but our code actually tends to lose money. Why do we lose money now? Well, what we introduced with this tiny little harmless change is we introduced the problem of unbounded concurrency. And if you're doing load testing, or let's say just a small test, you would probably not see it, because sometimes you just add 100 messages or maybe 200. But it happens when you have a lot of messages waiting in the queue, because this code, what it did, is essentially as many messages in the queue, it tried to fetch all of them, and it tried to execute the business code behind the scenes. And ideally, this would work if the code that we're executing has no limitations, but there is no limitations, right? Every code has limitations unless you explicitly design it to not have any limitations. But in our case, we're using the SQL Server, and the .NET has a concept of DB connection pools, and you configure it per application domain and so on. And a SQL Server DB cluster can handle up to a certain amount of connections. And once you run over the threshold, what's going to happen is the SQL Server will tell you, I'm sorry, but you opened too many connections. I'm going to throttle you. I'm going to do transaction timeouts. And then the problem is, once this effect happens, you're essentially losing the benefit of the message queuing system. One of the things why we're using message queuing system is, we could build a message queue in memory, right? We could do that. But once we do in-memory messaging, we're basically bound to the process, memory resources. And we use a storage-backed queue to be able to say, you know what, a storage has different scaling vectors. We can throw in more disk, expand the cluster, so we can offload the problem and load it when we have, and load and process things when we have time. But by introducing this tiny little change, we actually are losing all the benefits of a queuing system, because the code that is running behind the scenes is completely overwhelmed. And the weakest element in the chain, which in our case was the database, and I'm a bit unfair deliberately here to the database, because we all know that databases are quite scalable, but for the sake of this example, yes, it was a big problem. So let me show you this pretty quickly in a demo. I'm going to execute for 100 milliseconds the same code with the fire and forget without the wait statement that I showed you before. And on my crappy 8-core machine, while recording and while doing all sorts of other stuff, we can see in 100 milliseconds my machine is able to churn multiple 10,000 messages in 100 milliseconds. Obviously, this is a bit of an unfair example because I'm not doing I/O. Right? But you can imagine if you're using something like RabbitMQ, which can handle tens and thousands of messages per second, you would probably see a similar picture in your production system. Well, because we're engineers, we can solve complex problems. So let's put our sleeves back and try to solve this problem, try to fix it. So we said, well, wouldn't it be nice if we know the limitations of the DB connection pool. We can configure it. We can configure it to a certain number, but it would be nice if our message pump would actually stay within the limits that we give it, right? And that's usually the weakest element. It could also be, by the way, sometimes you have a third-party service that you're calling, and that third-party service says, you can do up to 200 calls at the same time. And you can do up to, let's say, 5,000 calls per hour. For example, if you're using the GitHub APIs. GitHub APIs actually introduces this rate limiting stuff, right? It's not different from what you already know, just applied here to queuing system. And then we said, well, we know a thing that is called a Semaphore or Semaphore Slim in .NET. So we introduced that. By the way, does everybody know what a semaphore is? Does anybody not know what a semaphore is? Please raise your hands. Okay, cool. So I will briefly explain it, just a really small explanation. So I usually explain a semaphore, it's like a toll lane on the highway, right? If you have 8 lanes on a highway and you have a toll lane, this is basically the semaphore, because what it means is only 8 cars can concurrently pass through the toll lane, right? So what it means is when all the toll lane gates basically are closed, it means the semaphore has acquired all its slots, then all the cars that are coming on that highway need to basically queue up behind on those 8 highway lines, right? And once a car passes through the toll lane, the next car can go into it and acquires it. And of course, there can be, with this example of 8 lanes of that toll lane, it can be that 8 cars concurrently pass through, or any number of cars up to 8 can pass through. That's hopefully a good enough explanation of a semaphore. And the Semaphore Slim is the more efficient variant in the .NET framework that is optimized also for async scenarios, because it offers a wait async method so that we're not blocking any thread. Anyway, so what we did is we introduced this Semaphore Slim, and we gave it a number of slots. For example, it could be the DB connection pool limit. Let's say the DB connection pool limit is 100. So we can set in the declaration of the Semaphore Slim here in the constructor, we can say you have 100 slots. Right? So up to 100 things can concurrently acquire the semaphore, and if the 101th comes in, the semaphore says, no, sorry, the toll lane is currently occupied. You can't pass through. Okay? So, and then what we do is, because we don't want to fetch stuff when we already acquired all the slots, we essentially do this await semaphore, wait async. So if the first consumer comes in and we still have 100 slots available, this code just falls through and executes this part. The second one falls through, and so on and so on. And the 100th one the 100 and plus one essentially acquires this wait async, and then it will just stay here and not receive anything from the queue. And then what we also need to do is, because we have the semaphore, we need to release the semaphore. And releasing the semaphore is basically the car is passing through the toll lane, right? So what we did is we introduced this try finally block, where we have the same code as before, then wrap it in a try finally, and only when the business code execution and everything is done, we then release the semaphore down here on this line. And that means other readers can pass through this code and fetch stuff from the code. With that, we can stay within the boundaries. And one other thing that we realized is, and that was the trade-off that we made at that time, maybe you're making other trade-offs, but we said, if we are shutting down, and let's say we have currently 5 messages that are processed, we want to give the code a graceful shutdown time. And graceful means we don't want to just kill the process in the middle of handling those messages, because there are all sorts of issues that can occur. We give it some time. So what we did is we basically canceled the cancellation token so that the cancellation can propagate through. And then there's a nifty little trick. Semaphore current count not equals max concurrency. You can basically idle loop over the semaphore to say, hey, by the way, when all the semaphore gates are released, basically the toll lane is empty, no cars are in there, then we know that we can shut down, and then we shut down. Okay, that's what we did. And this code, when you execute it, you can see that it behaves this way. So I set it now to a concurrency of 3, just so that it fits nicely the screen. So you can see that we only get packages of 3 coming in. Okay, so we have now limited concurrency. And this worked really nice. With the semaphore that controlled the floodgate, we were able to have a code that is there and was reliably pumping messages from the queue. But when time passed, what happened was, I mean, I was tasked to write this messaging abstraction, and I was really proud of it, obviously, right? We love to write infrastructure, or at least I have to talk for myself. I did love to write infrastructure code, and it was such a fun exercise. And whenever I could distract myself to not write business code, to not need to talk to customers, this is what I really loved at that time. But at some point, essentially, what's going to happen is I had this Mercedes-Benz, or let's say it for the sake of CO2 emissions, Tesla Model 3 in my mind, right? But I didn't really have time to really work on this all the time. And then my teammates started basically expand and change the code. Yeah, of course, I blame my teammates that everything went sideways. No, I'm just kidding. But so basically, it happens in all the projects, right? At some point in time, we had more and more pressure. We needed to deliver features, so we couldn't really extend this too much anymore. But still, because we had business requirements coming in, we had to make this code that we already had in place, what I call it flextensible, right? For example, we had cross-cutting concerns that we wanted to deal with. For example, for every message that is coming in, we want to log something. For every message that failed, we want to log the exception trace. Or we had business requirements, right? Whenever a message was successfully handled, we want to audit the message. Auditing the message means we can store it into a database, we can send it to another queue, stuff like that, business requirements like that. So the code started to look more like this. And I'm going to highlight it, what changed. This is the fetch and handle and release with middleware. And let's zoom a little bit in. So the code looked like this, and it's a whole bunch of stuff. But the important piece here is basically up here. Using var transaction, create transaction, we realized we actually need transactionality to communicate with the queue. Then we also realized, well, probably we need a child service provider because we need to resolve stuff from a child container per message handling. Then we had to introduce an abstraction, right? Because we can't just have static methods. We need to resolve classes of that type of iHandle message, for example, from the IFC container. And then for the auditing purpose, for the cross-cutting purpose, we needed an extensible middleware, which was func of handler context, func handler context, cancellation token, task cancellation task array, right? So that we could plug in different pieces into the puzzle. So basically, this code got more and more and more complex. And depending who you asked to, some people said, well, yeah, this is actually no longer really cool stuff. This is actually more like a rusty car because we bolted so much stuff on top of each other. Or some other people that said, well, all this concurrency stuff, all these fancy things, I don't really trust it. For me, it looks more like a banana car. And for other people that really love this code, that were thriving in this code, it looked more like this. And by the way, that happens when you procrastinate over a talk and you Google for funny cars, that you find pictures like that. Anyway, so I kind of hand-waved a little bit before the transaction part. But the transaction part is actually a really, really important piece of the puzzle if you're doing message queuing. And I call it life beyond transactions. Because when you start dealing with transactions, there are a few caveats that you have to take into account. Let's have a deeper look into transactions. In our case, like I said before, we used MSMQ in SQL Server. So, like I said before, code that we're executing under transaction handling is never side effect free. What it means is we're going to write stuff into the database. We're going to call potentially HTTP APIs, whatever. But we will also sending out messages to other queues, right? So the side effects will occur. Now, what happens on premise with MSMQ and SQL Server, when we create a transaction, we have a transaction scope that wraps this queue code. If we are lucky and if we know how to deal with it, there is this beast called Distributed Transaction Coordinator. And what the Distributed Transaction Coordinator did in our case, it was something really fancy. When you create a transaction with a transaction scope and you call into MSMQ, when you fetch a message and then you execute your code, and that code writes into the database, SQL Server, that supports the DTC as well, and MSMQ destinations that also support the DTC, it's going to escalate to a protocol that is called two-phase commit. And with two-phase commit, it's guaranteed that we only have exactly once delivery guarantees. Exactly once delivery guarantees means that we either successfully handled the message, the destination 1, destination 2 writes, and the database writes are successfully done, or nothing of that happened, okay? So that's exactly once processing when we commit the transaction. But there is a problem. The two-phase commit protocol has a lot of latency because the distributed transaction coordinator needs to coordinate with all the resources, here the queuing system and the SQL server, that are participating in that transaction. And that means a lot of latency. So once you start using this beast, essentially I can guarantee you that your throughput and performance will go down a multitude of times. And then you're basically saying, well, now we have the safety guarantees, but we actually need speed. How about we switch MSMQ out and we go to RabbitMQ, because RabbitMQ, I heard, is super cool and it's super fast. So when you do that, then we have other implications that are going to happen. So RabbitMQ doesn't offer what we call cross-queue transactions. RabbitMQ only has what we call a receive-only transaction. What it means is when you receive a message, the transaction is basically ACKing the message or NACKing the message. That's it. All other side effects will occur. That's receive-only transaction. So let me illustrate that with an example. So if we use RabbitMQ, what we can have is what I call partial updates. Partial updates means we're receiving a message, we have two concurrent codes executing, the green one here and the red one down there. The green one does some writing to the database. The red one tries to reach destination 1, destination 2, and the storage, and it holistically fails. We were lucky. But what happened was, we actually did an insert into the database. And then, because we failed, if we write our code right, we neck the receive transaction, which means the message rolls back in the queue and gets redelivered. And then you can see the picture. Any number of permutations of failure can actually happen in this picture, right? So that's what can happen with, for example, RabbitMQ. But there is also this concept of partial sends or ghost messages. Maybe you have heard that term. So what it means is, if we execute this code and not doing concurrent stuff, but we're saying we want to write to destination 1, that works. We write to destination 1, and then we lose the connectivity to the broker, for example. If you're lucky and your driver already has built-in retries, circuit breaker pattern, then it might be able to restore the connection, and then you're lucky. But if not, it fails, and what it means is that this part here essentially will not succeed. But destination 1 write actually succeeded. So what it means, if you have downstream consumers in this picture, those downstream consumers will receive a message that should never have occurred, because your business transaction is not completed. But of course, code doesn't live in isolation and stays always the same, right? The company that you work for, the customer that you work for, they gradually expand the system because it's making money. And at some point, because the data center is no longer cost effective that you're running on premise, maybe you heard that there is an amazing service in the cloud in Azure or AWS that you need to use, you start doing potentially a lift and shift paradigm where you gradually move into the cloud, right? Evolving the system. Well, I call it cloudy with a chance of failure. So once you start moving into the cloud, is that we have different transaction semantics again. For example, if you're going to AWS, Amazon Cloud, and you find this service called Simple Queuing Service, Amazon SQS. They also only have receive-only transactions. So if you're already on RabbitMQ and already have prepared your code to deal with that stuff, you're probably more or less good. But this time, the receive-only transaction is implemented in a different way. It's implemented with what they call message visibility timeout. A message visibility timeout is once you acquire a message from the queue for the timeout, let's say 30 seconds, the message is not visible in the queue. But if your code handling that message takes longer than the message visibility timeout, the broker will automatically make that message reappear. So what does that mean? Well, if you're writing code in your receive pump, you essentially have to write code per message that you receive to continuously change the visibility timeout of the message while your code is executing. Up to a certain extent, of course. And you need to make the right trade-off between, is it okay to redeliver and potentially duplicate the results? What are the business effects if we duplicate the results? So what are the SLAs to do so? Okay. And by the way, Azure Storage Queues, if you're in Azure, has the same concept built in. If you're using Azure Service Bus, then you're lucky, because Azure Service Bus has what we call sends with atomic receive. And sends with atomic receive in Azure Service Bus is implemented with a concept called send via headers. Many people don't know that this exists in the Azure SDK, Azure Service Bus SDK, but it's a pretty nifty feature. What's going to happen is when you have a transaction scope that surrounds your receive and surrounds the sends that you're doing, even if you're using multiple message senders in the code. And when you set the send via property, it's going to make sure that we have exactly once delivery guarantees, more or less, for the message that is coming in and for the messages that are going out. And it does it in the following way. You create a transaction, you receive the message from the queue, you execute your code, and then essentially you're saying, I want to send to destination 1. And you call the SDK, but the SDK basically sends it to the input queue attached to the incoming message. And then you say, I want to send it to destination 2. And then it sends it to the input queue as well, attached to the message. And then once you do your storage rights, and then once you say, okay, I successfully handled this message, you commit it, then the broker reliably, in an idempotent way, makes sure that you don't have duplicates, but it sends it to destination 1 and destination 2. And that's a guaranteed service that Azure Service Bus is offering you. Of course, you probably saw the picture down here. The storage write has happened, right? So that means your code still has to be idempotent when it comes to database writes. What does idempotent mean? Idempotent is basically just a fancy mathematic way of saying that the business effect should only occur once, right? If you want to bill a customer for $100 US, 100 euros, that transaction should only happen once. If that's the single atomic thing that should only happen once. That's basically idempotency shortly explained. So in essence, whether you use this fancy transaction mode or whether you use less fancy transaction mode, once you move in the cloud, you have to deal with idempotency. And the place where you put your code, your entity framework, save changes async, and all that stuff, it really matters. And it matters to a point where we can say, if you place the code in the wrong position in your C# file, it might mean that you're losing messages. And because we're talking about message intent, business intent capturing, losing a message means you're losing money in production, okay? So that really matters. So we talk now a little bit about the transactional guarantees. But let's look at another thing that people sometimes forget in the cloud. And Scott Hanselman called it penny pinching in the cloud. Well, what does that mean? Well, in the cloud, if you're using a SaaS or PaaS offering, you are usually charged by operations that you execute. So for example, if you're using Azure Service Bus, I think the first 13 million operations per month, they're free. And then for, I think, 87 million operations per month, you pay like per million operations, $80 US, okay? And you're getting charged by that. And 87 million sounds like a huge number, right? It's unbelievably huge. But if you calculate it down, it means for that price, you can do 120 operations per hour. And remember, we do receive and send. So that means at least we have 2 operations usually per message, which means we can actually do 60 operations per hour, which is not awful a lot. And we're getting charged for it, right? And then with Azure Service Bus, you're also getting charged, for example, for AMQP connections. So for 1,000 AMQP connections, I think they're included in the standard tier. And the more connections that you want, the more essentially you pay up to a certain limit. And of course, that differentiates between the tiers that you're going to use of your PaaS or SaaS offering. But things actually can get worse. And let's say if you write a bit naive code, for example, you're sending messages in a for each loop, what it means is every send message is an operation against the broker, against your SaaS PaaS offering. So what we are essentially trading off is latency and operation costs. Because every call that you're making to the cloud, even if you're in the cloud itself, right, has latencies. Of course, your cloud provider gives you SLAs and stuff like that, and you can usually count on them. Not always, but usually you can count on them. But what it means is the difference between doing 5 calls with, let's say, a latency of 10 milliseconds versus 1 call with a latency of milliseconds is 40 milliseconds. And also the operations. If you do five calls, you're getting charged for 5 operations, and if you just do 1, you're getting charged for 1. And that stuff can easily make a huge difference also from a business perspective, right? Because the money that your code earns has to be outweighed against operation costs, right? That's software architecture and software design. But so in essence, what we can say is instead of doing 1 call, we need to batch as many calls as we can into 1. But how do we do that? Well, the thing is, most SDKs nowadays, they have this concept of batching. But there are restrictions. Every cloud provider, because so that they can offer their SLAs, they're telling you, well, for example, with AWS SQS, you can give us 256 kilobytes per call maximum. If you're doing more, let's say on the standard tier, we're cutting you off. Then if you're in the premium tier, you can do 1 megabyte, but then you have to pay more. And then, for example, Azure Storage Queues can only do 64 kilobyte per call. RabbitMQ can basically do unlimited payload. You're only restricted by the amount of memory and CPU cycles that you have available in your cluster, right? But you have to do the capacity planning. And what comes into play is, for example, with Azure Service Bus, if you're using the send via feature that I explained to you, you have to write smart batching logic. What does smart batching logic mean? For Azure Service Bus, we can only put 256 kilobytes into one payload, and we have to group them by destination for the send via feature to work. So what it means is if we have 2 fat messages for destination 1, we can probably have 1 batch of 256 kilobytes. And then we need another batch for the other 5 messages that we want to send. And if we're sending 2 small messages to destination 2, we need to put them into another batch. But the good thing is, instead of doing, if I can count today, 9 calls, we are only doing 3 calls, right? So we actually saved 6 operation costs, and there is another nice little effect that we have here. Because we are batching, we have less latency, but we also have less likeliness for ghost messages to occur, right? Because everything is now in one call, so that means that's the unit of failure that we're now exposed to. So now we essentially have the basic bits. So we talked about sending, receiving, and transaction management, and that's usually what you need. But once you start evolving your architecture, you might want to do pops up. You don't just want to do just regular messaging, sending it into input queue. And once you're doing pops up, you're essentially forced to understand what the queuing technology that you're using is offering you. For example, AWS SQS or Azure Storage Queues, there are so-called simple queuing systems. Simple queuing systems means they only offer you queues. So if you want to, for example, have topics, it's not available. So, and for complex distributed systems, you might need topics to do pops up. So that means you need to write some infrastructure piece, some glue code that essentially manages that topology, so the mapping from a topic to a queue. For example, with Azure Storage Queues, you would need to use Azure Tables, table storage, in conjunction with Azure Storage Queues. Or with Amazon SQS, you would need to use Amazon SNS to combine it together. And you can imagine, once you have Amazon SQS and Amazon SNS, you have 2 services with different SLAs. And then you need to make sure that they communicate well together. Okay? Azure Service Bus has the concept of topics and subscriptions, but then you actually need to make up your mind how you're gonna do it. I'm not going to cover this part because of timing interests. I'm skipping it through. If you're interested and want to learn something from me about Azure Service Bus and what I call forwarding topology, feel free to approach me after this talk. So essentially what we can say is it all started with really simple code, but now we're living on the edge of sanity because like we heard, once we start doing a distributed system, we need things like pops up, we need topologies, we need to do competing consumers on queues, we need to manage state, we need to do routing, because we need to have a concept that says, if message X message X always goes to queue Y, and stuff like that. So we need to manage that configuration. But then there is also the human factors. I mean, code doesn't live in isolation. We need to make sure that we write the necessary documentation so that the people that manage this code actually know how to manage it and know the intrinsics of this code and how it behaves and why a certain code line is positioned on line 32 because it matters, right? Stuff like that is really important. And what happens when, for example, you're the smart person in the team, and what happens if you move on to another job? Are the people that stay around actually able to manage that stuff? And then what's often forgotten is this piece of the puzzle. Once you have a distributed system, I guarantee you also have a distributed systems mess, right? Because you have different pieces that are all over the place, and when something goes wrong, how do you know what went wrong? How do you troubleshoot what went wrong? So what it means is you need a way to monitor, to visualize what is going on in your system, and you need to actually be able to see whether certain type of consumers on your queuing system are still able to cope with the load so that you can fulfill the SLAs or the business requirements with your customers. And then there are also questions like the CEO comes to you and says, hey, we just acquired a new customer, I don't know, EasyJet. Can we handle the load of EasyJet in our production system? And then you give them a blank stare, right? You need to be able to answer questions like this. So what it means is we don't only need tools, but we also need to plumb the tracing stuff and the monitoring stuff and the visualization metadata, so to speak, into the code that we just wrote, into the sending parts, into the receiving parts. Topics like distributed tracing and stuff like that are really important. So, for example, we can connect up to New Relic, or we can connect to Application Insights if we're doing our Azure Monitor today, or we can use Prometheus and Grafana, but we need to essentially create that data as part of the message queuing infrastructure that we are writing so that we can leverage it when something goes wrong, or hopefully to predict that something will go wrong, right? So hopefully I was able to give you a good understanding of that message pump don't only start with code. There is much more than code that you have to think about. Hopefully I was able to give you a really good understanding so that you can make the right trade-offs. And I suggest try it yourself because I think it's a really good educational and learning exercise to write the message pump against your favorite queuing system of the day. And from that learning, whether you're going to use that in production or just do it as a side project or maybe as a, I don't know, in your team together, then you can decide whether you want to use it or not. But at least this knowledge gives you the ability to make the right trade-offs in your project, to either say, we're going to write it our own because we have those business requirements and we can actually deal with that complexity, or that you take something off the shelf. So you're hopefully now capable of doing that make or buy decision. Thank you very much for listening. So if you're curious and want to see a little bit more about the slides, the notes and everything, go to github.com/TonyMarbach/messagepump. I also have a bunch of business cards. Should you have more questions, feel free to either approach me directly in the hallways or grab a business card and shoot me an email should you have any questions. I'm also reachable on Twitter @DanielMarbach.